Section 12.1, magnetic forces and fields. Now, when we first taught you guys about forces and fields in Physics 20, you guys learned about gravitational fields because we all experience gravity. Then in Physics 30, we move into electric fields and magnetic fields. We noticed back when we learned about electricity, there's similarities and differences between electric and fields and gravitational fields. Same thing between magnetic fields and electric fields as well, although there's a much closer relationship, as we'll find out. So similarities include opposites. So for electric charges, you've got positive charges, you've got negative charges. You've got attractive forces, repulsive forces. For gravity, again, only attractive force. A magnet has two opposites. Does not charges, it has opposite what we call poles. Like it says, any magnet has two ends called poles, where the magnetic effect is the strongest. One pole we label as a north-seeking pole or N pole. The other we label as a south-seeking pole or an S pole. And the way we figure out which end to label N and S is we orient that magnet according to Earth's magnetic field. So a compass needle, for example, all a compass needle is a little magnet, and it's got a hole drilled in the middle, and it's allowed to rotate around on a pole, I guess. And what happens is it orients itself in Earth's magnetic field, the one that points geographically north to where Santa lives. That is called the North Pole, and the one obviously then points in the opposite direction would be called the South Pole. So, Earth itself is a big giant bar magnet, essentially. So, if we model Earth's magnetic field using a big magnet, and we know that all magnets on Earth point this way, point north towards where Santa lives, opposite poles attract and like poles repel. So poles that are attracted to this end of the Earth, labeled as a north-seeking pole, if we model Earth's magnet as a big giant bar magnet, there must be then a big S up there. And the way I sometimes get my students to remember that is S for Santa, that's where Santa lives. So all the magnetic fields, or all the magnets on Earth point in that direction. They're attracted to that direction. Notice that the geographic poles don't line up with the magnetic poles. So have you ever seen like a globe, for example, like a physical globe in a classroom or in a movies or something like that, where it doesn't spin around on a horizontal axis, it's slightly tilted. And that's to represent the tilt of Earth's axis relative to the magnetic field. They aren't the same. So when you say geographic north, you mean, like, for example, if you spin a basketball on your finger and it's going around and around and around on a horizontal plane, the axis of rotation would be a vertical plane through there. So that would be the basketball's north pole would be the top, north geographic pole. So if Earth's magnetic field, if you label that as the top, sort of, then the geographic pole, or the geographic axis of rotation, is at a slight angle to that. So how can we tell whether there's a presence of a magnetic field? For gravitational fields, you put a test mass inside that field, you let it go in the direction that it falls or moves due to a gravitational force. That's the direction of the gravitational field. For electric fields, remember that convention was we use a positive test charge, and the direction that a positive charge would experience a force, that's the direction of the field. Well, we can show that a field is present, a magnetic field is present, by using, for example, iron filings. So notice that we got a picture here of a magnet, and iron filings just sprinkled around that magnet, and we notice where the iron filings are most concentrated. They're most concentrated near the ends of the magnet, which we call the poles, where the magnetic effect is the strongest. We learned about field lines, right? Where the field lines are close together, that's where you've got a strong field. And when the field lines are far apart, that's when the field is the weakest. So the iron filings line themselves up on the magnetic field lines. Now, just like with positive charges and negative charges, you've got opposites. You've got a positive and a negative, and you had to pick which one we use as the test charge to define the direction of an electric field. Well, for a magnetic field, the north pole of a compass is the one that was picked. So the direction of a magnetic field is defined as the direction in which the north pole of a compass needle points. Even though there's no such thing as a magnetic monopole, poles always exist in pairs. So if you take the magnet and you break it in half, each end is going to have a north and a south. You break those halves in half, each end has a north and a south. You keep breaking a magnet again and again and again and again. Even when you get to one single atom, that atom will orient itself in Earth's magnetic field so that one end points north and the other end points south. And the reason why that is, it has to do with something called the spin of the electrons. I'm not going to get into it because I don't understand it completely, but the way how, like, for example, this is an oversimplification, but it's good enough for our purposes, where the Earth rotates or travels around the sun, and then the Earth is also spinning on an axis. Well, same model. If we can have a picture where the nucleus of an atom is the sun, and the electrons are orbiting around the nucleus, and each electron is also spinning on an axis, and it's not quite what's happening because electrons aren't balls and they don't really spin, but it's close enough. Spin is a property of subatomic particles that we use to classify them. We can use things like mass and charge. Another property is spin, which we don't really need for physics. Well, we don't need for physics 30. The symbol for a magnetic field is uppercase B, and we notice it's got a vector arrow over top indicating that you've got a vector. So it's got a direction, obviously. So the direction of the magnetic field is tangent to a field line at any point. So notice that if I was to have a north pole of a compass needle right here, call that a north-seeking pole, north would be repelled by north because like poles repel, and opposite poles attract. So notice all the field lines are pointing away from the north, and they make loops and go around and point then towards the south, because a south pole would attract a opposite north pole. This shape of a magnetic field here mimics the shape of Earth's magnetic field. So if I was to take Earth and then go like this, so Earth is like a big circle essentially. Hang on, I could probably do this shape. Shape. There it is. So we've got a circle. So here's the here's the Earth, and we'll move our Earth like that, kinda. And we'll make our Earth, say, yay big. So this is the shape of Earth's magnetic field. So notice, Earth is the big circle here. The magnetic field lines all point towards the north end of the Earth, geographic north. So the field lines, if you were to diagram the Earth's magnetic field, come from the south, geographic south, end up towards the north geographic end of the Earth. Okay, so what makes a magnet a magnet? So Hans Christian Ørsted discovered a long time ago that there is a very, very close relationship between electricity and magnetism. Come here, my dog barking. So we learned about electric charges. Stationary electric charges and a magnet had been shown to not have any effect on on each other. So if you have a positive charge, for example, or a negative charge, you bring a magnet towards it, there's not going to be any force between the two. However, Oersted found that when a compass needle is placed near an electric wire, the needle deflects as soon as the wire is connected to a battery and a current flows. So this was sort of an accidental discovery where as soon as he noticed he had a compass on his bench and he connected the two ends of his wires to some kind of battery, as soon as the battery was connected and charges started moving through the wire, then the compass needle deflected. So the moving charges, the moving electrons through the wire, the electric current, that caused the magnetic field around the wire. So we got a couple of different pictures here showing the shape of magnetic fields around wires. On the left here, we've got a straight conductor, and on the right, we've got, what if you take the conductor and you make it into a coil? A current passing through a straight conducting wire produces a circular magnetic field around the wire. So that is the shape of the field around the wire. The magnetic field lines are in concentric circles centered around the wire. So that's kind of weird looking because electric and magnetic fields aren't like that. But what if you take that wire and then you coil it up into a coil? Well, now what you get is what you call a solenoid. It produces what we call a dipole field, where you've got the shape of the field is very similar to that of a bar magnet. It's the same as a bar magnet. So the magnetic field lines come from one end of the coil and then go around and make concentric loops through the coil and then back out the other end. We're going to learn more about that coming up. Okay, so this is kind of the fun part for Physics 30. Left-hand rules for magnetic fields. So this is figuring out the relationship between the direction of the current and the direction of the magnetic field. So you have to do this. You have to make this shape with your hand. Wait a minute. Use my webcam. Like that. All right. So if a conductor is held in the left hand with the left thumb pointing in the direction of the electron flow, then the curled fingers represent the direction of the magnetic field. So if you point your thumb this way, your fingers curl around like that. If you point your thumb this way, then your fingers curl around like this. For Physics 30, we use electron flow as the model for charge carriers. However, if you look at a lot of other textbooks, not the one we're using, or websites, IB for example, they use something called conventional current. And conventional current is that the charge carriers are modeled as being positive instead of negative. We don't do that in Physics 30, but I thought I'd include it here because we'll deal with positives and charges moving not in a wire, but let's say protons moving through a magnetic field later on. But if you use positive charges as your charge carriers, then you use your right hand. If you have negative charges, then use your left hand. Okay. Now, sometimes we talk about these diagrams like right here. They're kind of hard to draw and hard to, draw on a piece of paper because they're 3D diagrams and I'm terrible at drawing. And sometimes we turn a 3D diagram into a 2D diagram like this, where we take a wire, and a wire obviously is a cylinder, but basically you turn the wire like this, and you take a cross section of the wire, then it looks like a circle. So same rules. We're going to learn a couple different symbols here. So normally in physics we use like arrows to go to the top of the page, bottom of the page, left, right, whatever. But now we're going to learn about the X and the dot. If you see an X in the middle of this cross section of the wire, then that means the current is flowing into the page. So X means into the page, and a dot means out of the page. So what you do is when you see a diagram like this is saying that you've got a cross section of the wire where the current is flowing into the page. So what you do is you take your thumb and you point it into the page, and now I'm doing it into the screen, and notice my fingers curl around, I do it like this, my fingers curl around in a counterclockwise fashion. And notice the magnetic field is represented by these little compass needles. So the compass needles will point. Here it's pointing to the left, here it's pointing to the bottom of the page, here it's pointing to the right, here it's pointing towards the top of the page. So the circular magnetic field line represented by these different compass needles here is directed in a counterclockwise fashion. For the diagram on the right here, we've got current flowing out of the page. So out of the page, you do this. The thumb is now pointing out of the screen. I'm doing my face. So if the thumb is pointing out of the screen, notice my fingers are then curling around in a clockwise fashion. So if I was to place a compass needle above the wire right here, it'd be pointing to the right, and then down and to the left and towards the top of the page. So now we've got our magnetic field in a clockwise direction. Whereas if I move my hand around like this, then it's counterclockwise. All right. Now, what if you've got a coil? This is sometimes what we call the second left-hand rule, or the rule for coils. So you take that straight wire and then you wind it in a coil. What happens is you get a differently shaped magnetic field. You get a dipole field. So it's a different rule. So if a coil is grasped in the left hand, with the curled fingers representing the direction of electron flow, then the thumb indicates the direction of the straight magnetic field within the coil, or it points to the north pole of the solenoid. So here we've got wires wrapped around this core, and the electrons are flowing like this. They're going sort of up the front and down the back, and then up the front and down the back. So you put your fingers up the front, down the back, and notice your thumb ends up pointing to the right. That is the direction of the magnetic field line. So what we have is the field lines would go around, I don't know if I can draw very well with the mouse, like this. And then, oh no, that's the magic pen. Never mind. The field lines would go around like so. Actually, I can just do this, can't I? Pen. Like so. So we'd have this. Actually, not bad. So the direction of the magnetic field would be to the right through the coil, like that. And then the magnetic field lines would be going around like this. So I'm just going to draw one of them. And then back towards here. So notice this would be then the North Pole, and this would be the South. So your thumb ends up pointing towards the North Pole of the solenoid. So another picture I found on the interweb somewhere. Here we've got a battery at the top here, small line, negative terminal, big line, positive terminal, and the electrons are flowing out like this and like that, and then down the front of these coils and then up the back. So the person is grasping the coil where his fingers are following the direction of the electron flow, and then the thumb points toward the north end of the solenoid. For conventional current, another diagram I found somewhere, use your right hand. So we're not going to test you on conventional current because it's not part of the curriculum. However, if you're doing Google searches or watching YouTube videos or something like that, sometimes IB especially, they talk about conventional current, and don't get confused basically because they'll be using their right hand instead of their left hand. So we notice, I can tell this is a conventional current from this diagram when I found it, because notice that it shows the positive side of the battery on the right here, negative side of the battery on the left, and the current is coming out of the positive side and going to the negative side. So the person is using their right hand in order to figure out the direction of the magnetic field through the coil. Okay, so now I've got some examples of current carrying conductors wrapped around an iron core here. It doesn't have to be iron, but just a tube.
wrapped into a coil. And we'll practice using the second left-hand rule to figure out the direction of the magnetic field in and around the coil. So what we do is we first take a look at our battery here. And the shorthand notation for batteries is that the negative terminal is the little line and the positive terminal is the big line. So the electrons would come out of the battery, be repelled by the negative, and go around the wire like this, and then towards the positive, like that. So now we tend to grasp the wire, grasp the coil, I mean, with our left hand, with our fingers curled in the direction of electron flow. So our fingers would then go up the front and down the back. And that leaves our thumb pointing to the right. So that means this is the north pole of the solenoid, and that's the south pole of the solenoid. Okay, and that's just as simple as that. Let's try it a few more times here. Notice the diagrams here. We've got different coils and we've got different batteries. So one thing, the reason why I do this is to want to show you guys that uh, some students will decide, oh, they'll figure out some kind of rule or a pattern where, oh, the north is always on the negative, the south is with the positive, whatever. That's not a thing. You kind of have to do it from scratch because it depends the way your wires are wrapped and the way the battery is drawn. So let's just practice. So let's try another one. We've got our positive terminal here and our negative terminal there. So our electrons would be coming out of the battery to the right. So they'd be going up the back and down the front and then towards the positive terminal. So now our thumb points in the other direction because if we wrap our fingers around the coil where our fingers are up the back and down the front, now our thumb is pointing this way. So that's the North Pole. A couple more times here. So here we've got the negative, got the positive, electrons coming out of the battery to the right. So this time you're going up the front and down the back. So you grasp the coil with your left hand, up the front and down the back, and our thumb ends up pointing this way. So that's the north-seeking pole of the solenoid. And one more. So here we've got the negative on the left, positive on the right. Electrons are out of the battery towards the left-hand side here. So the way the wire is wrapped, the electrons will go up the back and then down the front like this, and then towards the positive terminal of the battery. So if you wrap your fingers with your left hand up the back and down the front, then your thumb ends up pointing to the left. So that gives us that the North Pole is on the left.
Okay, so why is one piece of metal like you can magnetize it? Like why can you stick a magnet to like the filing cabinet, but maybe not to the leg of the chair or something like that that's made out of aluminum? Well, out of all the metals on the periodic table, there's only four that are magnetic, and their term is ferromagnetic. Um, they are iron, cobalt, nickel, and gadolinium. Gadolinium, you may not hear of gadolinium very, very commonly. Usually people say iron, nickel, or cobalt. Gadolinium is actually not magnetic at room temperature. You have to cool it down significantly below room temperature before it becomes magnetic. And we'll talk about why that is in a second. For example, a piece of iron. You could have an iron that is magnetic and another piece of iron that is not magnetic. So why is one ferromagnetic material magnetic, a magnet, and the other one isn't? And that has to do with domain theory. So microscopic examination reveals that a magnet is actually made up of tiny regions called domains. So each little region inside any piece of ferromagnetic material, and that's iron, nickel, cobalt, gadolinium, not aluminum. Aluminum or copper or silver or gold, metals that aren't magnetic don't have domains. But in a ferromagnetic material, you've got tiny regions called domains, and each domain behaves like a tiny magnet with a north and a south pole. So if these got these non-magnetized, in a non-magnetized piece of iron, like say like a paper clip or something like that, the domains are arranged randomly, so basically they cancel each other out. But if you might have noticed, if you bring a magnet towards a bunch of paper clips, you can pick up a whole bunch of paper clips and they become what are called temporary magnets. What'll happen is, in the presence of the external magnetic field, that magnet that you use to pick up the paper clips, some of the domains will line up in the same direction, so indicating the direction of the magnetic field. So notice they're pointing this way, and then if we were to make a complete loop, they would go around like that. So if they're pointing that way, this is the north and that's the south. So in a permanent magnet, like ones that you can, stick to the whiteboard or whatever, some of the domains are basically lined up in one direction. The more domains that are aligned, the stronger the magnet. So gadolinium, for example, like we talked about, you have to cool it down. We know that thermal energy in a solid especially has to do with atomic motion. So the atoms of the gadolinium are vibrating back and forth. At room temperature, the atomic vibration is such that it randomizes the domains of the magnet. Whereas if you cool it down and the atomic motion slows down a little bit, then for gadolinium you can get the domains to orient themselves, and the gadolinium is then magnetized. Okay, so that is it for section 12.1. I recommend for sure reading the textbook, especially in this environment with our online learning. Q&A will come later during office hours, but for now, just a few questions for homework on page 592, numbers 4 to 8, 11, and 16.